All right, welcome back, everyone. Our goal this week is to start talking about proofs, which are going to be one of the bigger pieces of the course overall. And throughout this class, we're going to talk about a variety of different proof methods which are suitable for a wide range of problems. But we're going to start with what is the most basic sort of proof, which is what's going to be called a direct proof. So direct proof is going to be used to prove statements that look like P implies Q, which is pretty broad because it also includes things like if P, then Q. Then includes stuff like if X is an element of the set A, then whatever. But then that's just a fancy way to say for all X in A, blah, blah, blah. So all of these are really just different framings of an implication, and with direct proof, we're going to have at least a hope of proving statements that look like this. So what is our proof of P implies Q going to look like? What is our outline here? So our outline here is that at the start, we're going to suppose that P is true. Now, that might seem like a weird place to start because we don't know if P is true. But here's the thing. If I go back to the truth table for implies, if P isn't true, that is to say, if P is false, that means I'm in this lower half of the table. I'm down here somewhere. And in all places in this lower part of the table, the implication's true. So, in fact, actually, the only part that's interesting, the only part where something could go wrong, is in the instance where P is true. So really what we have to do is, in the universe where P is true, we have to somehow get to the fact that we're actually in this first line of the table and that we're not in the second line of the table. Here's where I get a bit vague. So then we're going to do some stuff, aka math. This is where the math happens. And then at the end of that stuff, hopefully, we're going to get to, and therefore Q is true. And this, therefore Q is true, is exactly telling me that as soon as I'm above this line, I'm automatically in this case and not this case. And so what that does is exactly rule out the possibility of the one way an implication could be false. That is roughly the way we are going to follow direct proof. Let's go through and do some examples. So let's prove that if we start with an odd integer n, then 3n plus 1 is even. So, what is this? So this is an implication. So if n and z is odd, then 3n plus 1 is even. So in my rubric, this is the thing I called P. This is the thing I called Q. So when I go to write down my proof, I'm going to start with supposing P. That is, suppose that n is in z and n is odd. Note, by the way, n in z is odd is just shorthand for n is in z and n is odd. This is a perfectly fine shorthand to use, but I just want to spell out that's exactly what it's saying. Now, I want to go through and somehow work with this. I want to somehow expand from here and get to the point where I can say something meaningful about 3n plus 1. How am I going to do that? Well, one key thing here is that I have used the word odd. And because this is a vocabulary word, and indeed it's a vocabulary word that we talked about last video, I can go ahead and replace this word odd with its definition. Reminder, what's its definition? That's here. We say that an integer n is odd if there exists k and z such that n equals 2k plus 1. So thus, by the definition of odd, there exists some k and z such that n equals 2k plus 1. All I did there was to copy out the definition word per word that we agreed upon in the previous video for odd. Now, mathematicians sort of implicitly agree that when I write there exists k and z such that n is 2k plus 1, that I've now chosen such a k. Remember, there exists k and z such that n is 2k plus 1 means there's at least one, but maybe many k's such that this is true. But when I write this statement, now when I reference the letter k, I'm going to be talking about a particular one of those k's such that n is 2k plus 1. Okay, so I'm going to write in parentheses, so this is not something I would write in the actual proof. But just when mathematicians say there exists such a k, implicitly this fixes such a k. But now, what is it I really want to think about? I really want to think about 3n plus 1. And so, why do I want to think about 3n plus 1? Because in my rubric here, I'm trying to get to, therefore q is true. And q is a statement about the number 3n plus 1. So I have to think about the number 3n plus 1. Now, the word we math folk like to use for, hey, here's the thing I want to think about it, is consider. So when someone in a proof writes the words consider 3n plus 1, they're just saying, hey, here's the thing that's not part of what we were thinking about it, but I'd now like to think about it. And what am I going to do? I'm going to put this thing I'm considering together with the one fact that I know. So I substitute in 2k plus 1 for n, and then I do the algebra to write out what 3n plus 1 is, which is that it is 6k plus 4. Now I would like to go through and finish this proof. So I would like somehow to be able to identify that this number is even. Well, how am I going to do that? Well, in order to do that, I need to look up the definition of even, which is that we say an integer n is even if there exists a k and z such that n is 2k. That is just, it's 2 times an integer. So I want to show I can rewrite this number, which is the same as this number, as twice an integer. No secret, the integer that this is double of is 3k plus 2. So I give a name to this thing, just so I can write that, hey, 3n plus 1 is 2m. And so 3n plus 1 is even, because I've now shown exactly what I need to show in order to show that this thing is even. Please note, I cannot use the letter k here. I definitely can't show that 3n plus 1 is equal to 2k. Even though the definition says 2k, I can't do that. Why? Because I've already decided that n is 2k plus 1, so I would be trying to show that 3n plus 1 is 2k, but 3n plus 1 is 6k plus 4, which is not going to be 2k. So I have to choose a different letter. So, moral of the story here, the letter that gets used in one of these definitions is not relevant. I can replace this k with any particular letter, and so in this case I happen to replace that k with the letter m. But now I have followed the rubric. I have supposed the if part. I have then done some math. In this case, that math amounted to writing out the definition of odd, then doing a small amount of algebra, and then repackaging that algebra into the definition of even. And then I have gotten to the statement that q is true. And that's exactly the formula I want for a direct proof, and so I am done. And the traditional way to celebrate the completion of a proof is a proof box. That means we have proven the thing we were supposed to prove. Just for emphasis, I want to go over what this proof said in some particular case. So here I supposed that n was in z and n was odd. Let's suppose, for whatever reason, let's take n is 19. N is odd, so there exists a k such that n is 2k plus 1, and in fact that k in this instance is 9. And again, all the proof was saying was because this number was odd, I could find such a k. In this case, such a k is 9. And then we said, well, now consider 3n plus 1, which in this instance happens to be 58. And my claim here is that from the algebra, we can show that this thing is actually the same thing as 6k plus 4. Is that true? Well, 6 times 9 would be 54, plus 4 would be 58. So we should believe this equals already, but we can check that our proof really works. Really, it is the case that for this k equals 9, and this n equals 19, if I calculate 3n plus 1, it really does work out to be 6k plus 4. So then, if m is 3k plus 2, which in this case happens to be 29, then 3n plus 1 is 2m. Namely, what we're saying here is that 2 times 29 is 58. And thus, 3n plus 1 is even. So really, our proof here amounts to a Mad Lib, where we get to suppose that n is blank, that's odd, and so we're told, okay, well, since this thing is odd, I can find a matching k so that this thing is 2k plus 1. Then I'm supposed to let m be 3k plus 2. Note, I've already picked k. And then I should see, as long as I've done everything right here, that 3n plus 1 is 2 times m. And so that tells me that 3n plus 1 is even. So pick your favorite odd number. Then there's a k, such that this thing is 2k plus 1. So that would be 81 in this instance. So then let m equal 3k plus 2, which would be 245. And then we just check that really, in fact, 2 times m, which is 490, is the same thing as 3 times n plus 1, which is slightly harder to check, but in fact is 490. So really, the way I should think of this proof is that I've written out a proof for every case simultaneously in the sort of Mad Libs format. And so by doing that, I actually know now, as long as I believe my argument, that no matter which odd number I start with, I always end up with an even number if I triple it and add 1. Let's do something very similar. Let's prove that if I start with an odd integer n, and then I calculate n squared plus n plus 1, that the thing I get is also odd. Our proof here, of necessity, starts with supposing that n in z is odd. Again, if we're doing a direct proof of an if-then statement, we start with supposing the if part. If you have a definition you can use, this is usually a good time to use it. So in this case, we're going to use the definition of odd. So we've again written out the definition of odd here, applied to n. And so, again, we've implicitly chosen a k here that makes this true. And so now we want to look at this n squared plus n plus 1. And again, here I'm using the word consider. There are other ways, but basically saying, focus your attention for now on this quantity. And I know I need to look at this quantity because that's what's involved in the thing I'm trying to prove. Now we get to follow our noses using algebra, saying, okay, I know I can write n as 2k plus 1, and so I could rewrite this in terms of k, so let's do this. And I'm going to let this continue on to the next line, which you should usually not do if this is typed. If you can at all avoid it, you can just put a new line here to drop onto the next line. But on paper, especially when I'm writing this big, there's not always an option, so we're just going to make do and see, okay, hey, this thing is 4k squared plus 6k plus 3. Now I want to show you that this thing is odd. So that is, I need to show you that this thing is 2 times something plus 1. So I'm going to go ahead and pick my friend L here to be 2k squared plus 3k plus 1. Then n squared plus n plus 1, which we showed already is 4k squared plus 6k plus 3. It's the same thing as 2l plus 1. And so n squared plus n plus 1 is odd. And so that is how these proofs are generally going to work. I'm going to encourage you to practice doing one of these yourself before we do it together. And this time, I'll write out almost exactly the same thing, except I will change it to n and z being even. And after I've done that, then I will let you fill in whether this thing works out to be even or odd, and write up a similar proof. Okay. But again, I really recommend pause, try and do this yourself, make sure you understand what you're doing, and then compare to what I write down in a minute. Okay, so what's the answer? If n and z is even, what is this thing? Well, hopefully you agree with me that the answer here is odd. How do I know that? Well, I could, for example, if I believe that the answer is going to be either even or odd here, I could just choose an even number, like, say, 2, and calculate 2 squared plus 2 plus 1, which would be 7, which is odd, and then I know that this has got to be odd. And so that doesn't prove anything, but it at least tells me this is probably what I should guess. So let's try and prove it. To start, we're going to suppose that n and z is even. Thus, there exists k and z such that n is equal to 2 times k. That's just the definition of even. We can then go ahead and consider our n squared plus n plus 1, which is the same as 2k squared plus 2k plus 1, which is that. And so if I let L be 2k squared plus k, then n squared plus n plus 1 is 2l plus 1, and so n squared plus n plus 1 is odd. That is what we wanted. Proof box. Aside about LaTeX, by the way, whenever there's k's, the natural letter to pair with a k is an L, but the usual font for an L looks exactly like a 1, and so is morally speaking useless. This loopier form of L is always available to you in LaTeX as \ELL, just the word L written out. I recommend this. It's one of my most used LaTeX variables, especially for this kind of calculation. So keep that in mind. Use it if you will. Now, I want to point out we've actually proven something a little bit cleaner than either of the things I wrote out before. Because we actually proved if you start with an even number, and then you do this operation, you get an odd number. But we also proved that if you start with an odd number, and you do this operation, then you get an odd number. So those are the only two possibilities. And so we've actually proven something fancier. So we've proven that, in fact, we don't need to make any assumptions about the parity, that is, the odd/evenness of n, in order to show that n squared plus n plus 1 is odd. Okay, n squared plus n plus 1 is always odd. And this is a little bit of a hint as to why some of this is a bit more subtle than it at first appears. Because if the question I had originally given was, prove that if n is in z, then n squared plus n plus 1 is odd, it would not have been super clear where to start. We could have said, well, suppose n is in z, and then we kind of would have been stuck. In fact, in order to really make progress, we would have had to next think, okay, well, what happens if n is odd? What happens if n is even? Which are the things we ended up doing, and then sort of put those together into one mega proof in order to get this kind of statement. So thus, a lot of these proofs we're going to be writing down are fairly straightforward, but be warned, there's often some subtleties lurking around the corners. Now, I'm sure there's someone out there who's thinking, why did we even bother doing this? I know that if you take an odd times an odd, it's odd, and so if you then add an odd to an odd, you get an even. So why did we bother writing all of this out when I could have just said, okay, odd times odd is odd plus odd is even, done. And the reason is that we want to be careful that we practice these skills while we have a good intuition for what's going on. So we're not going to use any of these facts about odd times odd is whatever, odd times even is whatever, odd plus even is whatever. We're not going to use those unless we prove them. And so we want to be careful, again, just to practice this structure of proof. But if you want to think in those terms, we certainly can practice writing out proofs of those more general things. So namely, let's prove that if x and y are odd, then x times y is odd. That's just one of these statements that I'm betting you've known for a long time. But let's prove it just using our definitions. Again, I recommend pause the video for a minute, think about it, and then come back and watch. Okay, so hopefully you're not too surprised. The first line I'm going to write is suppose x and y in the integers are odd. And I need to apply those definitions. Here's already an area where I can make a pretty serious mistake. Namely, the definition of odd is there exists a k such that this thing is equal to 2k plus 1. But again, make super sure it's not the same k for both of these. So what I really need to do is pick two different variables. In this case, I'll pick k and l, and say I'll choose those to be integers, where now I want x to be 2k plus 1, but y to be 2l plus 1. Again, I just want to make sure you see, if I assume x is 2k plus 1 and y is 2k plus 1, I would be assuming that x and y are equal, which certainly is not a thing I'm allowed to assume. So always be careful with these things. From here, we can follow along with basically the kind of thing we've done before. So we can look at x times y. That's going to be 2k plus 1 times 2l plus 1. And if I write that out, that'll be 4kl plus 2k plus 2l plus 1. And so we want to show this number is odd. Okay, and so I want to show that this is twice something plus 1. So if m is 2kl plus k plus l, then x times y is 2m plus 1. And so x times y is odd. And there we get our little proof box. So really, from our definitions of even and odd, we have almost enough information to prove all the facts we know about even and odd integers. Next up, let's prove this. That if I start with an integer that's greater than or equal to 2, and I calculate that integer cubed plus 1, the answer is always composite. Now, before I talk about this, I want to just make an aside that if I instead looked at n squared plus 1, this is believed to be prime infinitely often. For example, if n is 2, this works out to be 5. If n is 4, this works out to be 17. If n is 6, this works out to be 37. If n is 10, this works out to be 101, and so on. There are lots of primes in this polynomial, and indeed we conjecture but can't prove that in fact it gives you infinitely many primes. But in contrast, we are claiming that this formula gives you no primes. Well, except for 1 cubed plus 1, which is 2. How can that be? It's really helpful here to go back and remember my definition of composite. Namely, a positive integer n is called composite if there exist integers k and l such that n is k times l, and both k and l are greater than or equal to 2. So ultimately, to show that this number is composite, I'm going to have to prove that there are k and l that multiply together to be this. So what are those k and l going to be? Well, in fact, they'll be these. If I take k to be n plus 1, l to be n squared minus n plus 1, then I'll let you do a tiny bit of algebra to check. N cubed plus 1 is k times l. And what I have left to do is to argue that both k and l are at least as big as 2. Because remember, if one of these numbers happens to be 1, I definitely haven't shown that n cubed plus 1 is composite. So k is easy. Since n is greater than or equal to 2, k is in fact greater than or equal to 3. So no problem there. For L, it's a little bit trickier, but I can still show you that L is at least as big as 2 if I write L as n times n minus 1 plus 1. And then, since n is greater than or equal to 2, both n and n minus 1 are at least as big as 1. So n times n minus 1 is at least as big as 1. And so n times n minus 1 plus 1, that's at least as big as 2. So L is at least as big as 2. And now, since I've shown you that I can write down a k that's at least 2, or in fact at least 3, and an L that's at least 2, that multiply together to be n cubed plus 1, I've shown you that n cubed plus 1 is composite. And so this is done. Now, the astute among you will have words about this proof. Namely, you might say, okay, well that's great. I agree this is a proof, but where on earth did these things come from? And so this goes back to a point we talked about in the last video, which is that in order to prove a there exists statement, which being composite very much is, all we have to do is write down an example, which means that all we have to do is find an example. And now, on the one hand, you do have to prove that it is an example, but you don't have to justify how you found it. So definitely you have to show that if you multiply these two things together, you get n cubed plus 1, but you don't have to show where that came from. Now, of course, if this is on the homework, you have to figure it out. So how do you figure this out? And this is where you're going to learn that an awful lot of the homework is going to require scratch work that no part of is going to make the final version of the homework you turn in. So there's going to be lots of scratch work going on, and at the end of the day, you're going to turn in proofs that are often going to be very short. And I want to remind you, and I'll remind you a lot of this throughout the course, the length of a proof has very little to do with the difficulty of the proof. There are many one-line proofs that are incredibly difficult to find, and there are many page-long proofs that are really very easy. And that has to do a lot with what work do you actually have to show to make something a proof, versus what work can you do but that you don't actually have to show. So let's go over this. How would you possibly figure out that n cubed plus 1 is n plus 1 times n squared minus n plus 1? And I think the easiest way to do that is to make a table like this and look for patterns. And why are we doing this? We're just collecting a little bit of data to try and guess what it is we're trying to prove. Now, when you write down this table, you might notice there's a lot going on. There's a lot of things that you could look for here to try and see some amount of insight into how this is going to look. But a thing you'll notice after not too much time is that n plus 1 always seems to be a divisor. 2 plus 1 is 3, 3 plus 1 is 4, 4 plus 1 is 5, 5 plus 1 is 6, 6 plus 1 is 7, 7 plus 1 is 8. Once you notice this from the data, then you say, okay, n cubed plus 1 is going to be n plus 1 times something. What's the something going to be? Well, I actually know a fair bit about this, because together, these things have to give me an n cubed, so that better mean this is an n squared. And likewise, this plus 1 here had better match that to make that a plus 1. And so, in fact, actually, the only thing I don't know here is what this coefficient is on the n in this term. And so you can actually go ahead and figure all of this out by multiplying this out. And when you do this, I've just named the coefficient here a, you'll get n cubed plus a plus 1 n squared plus a plus 1 n plus 1. but I want this thing to be n cubed plus 1. And so that means I need both of these things to be 0, which means I am solving a system of two equations in one unknown, but the two equations are a plus 1 equals 0 and a plus 1 equals 0, which fortunately has the solution a equals minus 1. And so once I see that a is minus 1, that is how I uncover that n cubed plus 1 is n plus 1 times n squared minus n plus 1. So again, no one expects you to notice or see this right away. You have to sort of pull this out of somewhere after looking at some data, trying some examples, figuring out what's going on. But once you figure it out, all this work that we had to do in order to find this factorization is not actually part of the proof. It's not part of the work of demonstrating that this number is composite. So we leave it out. You'll notice this is a general trend among mathematicians writing proofs. We generally try to avoid including extraneous information. Which is not to say you have to be as terse as possible. You definitely don't have to try and use as few words as possible. I'm not encouraging that. But you want to make the logic as clean and clear as possible, which means you want to put unnecessary stuff outside of the proof. And so, if you want to explain how you came up with something to the person who's reading your proof, that's great, just don't put it in the proof. Alrighty, I'm going to wrap up this video here for now. I'll come back in the next video, and I'll give you a bunch more examples of direct proof that show up in a bunch of different other types of contexts. But that's all for now. I'll see you next time.